connection between the Heun equation and Liouville conformal field theory. And there is a number of connections between linear ODEs and Liouville test. So the first probably was due to Zamolodchikov. There is no point. Okay. Due to Zamolodchikov in 1986. Zamolodchikov has related the accessory parameter in Heun equation to quasi-classical limit of Virasoro conformal blocks. Then, there is another connection now to, so this corresponds to central charge which goes to infinity. Another connection relates conformal blocks is equal to 1 to Liouville functions and associated linear system. And like most recently, there was a new connection discovered, which I will mostly talk about. Very recently, the connection problem for Heun equation was conjecturally solved in terms of, again, quasi-classical conformal blocks by these people, so Tanzini, Bonelli, and their PhD students. And also there were very much related results to that, which were obtained on the gauge theory side by Zhong and Niklaus. So at the practical level, so this conjectural solution gives us a perturbative expansion connection matrix in a suitable parameter. And so the goal is, the goal of the talk is, well, we want to understand how these perturbative expansions can be obtained without safety. But somehow I want to explain this relation first. So the logic of the story will be somewhat opposite to some of the previous talks. So we will start with a kind of quantum monodromy. Monodromy of Liouville conformal blocks with respect to positions of degenerate insertions. So this is an operator valued monodromy involving shifts of intermediate momenta. And then, this Heun connection problem will arise in the quasi-classical limit of that. So we go from quantum to classical. Okay, so let me introduce the main actors here. So we will be interested in the it doesn't fit on the screen. Okay, so we'll be interested in essentially Schrödinger equation of this form with a particular rational potential. So the relevant quantity is the quadratic differential V of z squared, and so in like for the purposes of the talk, so this quadratic differential will only have second-order poles on the Riemann sphere. So the most basic example corresponds to 3 second-order poles. So this is a geometric equation, right? So this is the most general expression that you can write for the potential. So you have this growth at near z equal to 0, z equal to 1, and z equal infinity. And if we have, let's say, 2 second-order poles, then basically this and this drops out, and we have Euler equation. Okay, and then we can consider Frobenius solutions of our Schrödinger equation. So this distinguished basis of solutions which diagonalize the operator of analytic continuation around the relevant singular point. So we have 3 such distinguished bases. here I write two of them, and well, there is some formula involving hypergeometric function, but this is not really important. What is important is that so we have this fractional powers determined by the local monodromy exponents, and then we have a holomorphic function, well, with the series starting with 1. So we have some kind of normalization. And so the question, the main question that we ask is, well, how to relate these two bases, and, well, the elements of the corresponding connection matrix, they can be expressed in terms of just a single function, which I call C here. So this is precisely related to, this is why I write the hypergeometric equation in a somewhat non-standard form, in the normal form. So you see, flipping this local exponents is a symmetry of the equation. But it's not, it doesn't leave the Frobenius solutions invariant. And so this symmetry allows you to reduce finding the connection matrix to determining just one single function. And in the hypergeometric case, so this is a very well-known expression in terms of gamma. Okay, so basically what we now want to find is an analog of this connection matrix, but for a more complicated equation, where now we have 4 regular singularities. So just as before, we have this characteristic terms corresponding to second order poles at 0, 1, infinity, and so there is a 4th singularity at t. But now there is one extra term that we can add without spoiling this singularity structure. And so in this term we have a new quantity called accessory parameter epsilon. So this is not fixed by local monodromy. So it, of course, it influences the global monodromy of the equation, but this is something that we have in addition to local. And for later purposes, we will assume that so this 4th singularity lies outside the unit circle. So this involves, of course, almost no loss of generality. If it's not the case, just do the Möbius transformation. Okay. Right. So now the space of monodromy data associated to Heun equation has this familiar structure. I think it has already appeared in several talks previously. So we have here 4 tuples of matrices in SL2C that are multiply up to 1, which have fixed eigenvalues and which are considered up to overall computation. So this is a 2-dimensional space. And so the parameters epsilon and t, so the position of the 4th singularity and accessory parameter, can be viewed as some kind of local coordinates on this space. Another possibility is to introduce coordinates on M, is to use this trace functions associated to different closed contours on our punctured sphere. So like, for example, so one particularly important parameter in what follows is this sigma, which is related to the monodromy exponent corresponding to this cycle going around the pair of points 0 and 1. Okay. And so now, well, in this monodromy theory of linear ODEs, basically there are 2 like basic questions. One, so given an equation, we want, so basically given the data such as epsilon and t, we want to compute monodromy data, or we can fix the monodromy and ask ourselves, is it possible to produce an equation which has this specified monotomy. And these questions are highly non-trivial because, of course, this map, Hilbert map from equation to its monodromy, so it's highly transcendental, right? And even, for example, the image of the map, I think it's an open problem to characterize it completely. So this map, for example, is not surjective. But, so if you fix a sufficiently generic monodromy, then in principle you should be able to find an equation which has such.
One stupid question. This monodromy data is always for like this 4 punctures here, or you can also like the example that we had before. Is it like always you need this? I mean, this is always just the case where you have, or you can have also for pairs of primes. Can you have just pairs of primes?
You mean in Heun equation or in some general?
In general.
Well, there are no, so to say, moduli associated to pairs of pens because, well, basically, in higher rank you would have some additional coordinates sitting inside the pen, but not in rank 2. But I'm sure.
In general, I want to see what is there.
No. So in general, of course, in addition to this, exponents of composite monodromy, and so in addition to this Fenchel-Nielsen type coordinates, there will be some extra coordinates sitting inside each pair of pens, but not in this simple case. Okay, and so first let me say a few words about the direct monodromy problem, which can be formally solved, in fact, for basically arbitrary potential V of z, and this was done more than 1 century ago by Heun. So the idea is that, well, inside the annulus, absolute value of z between 1 and t, so we expand the potential in the run series, then we fix the basis of solutions which diagonalize this composite monodromy along this cycle here. So again, this will be given by some kind of Laurent expansion up to this fractional power, and then our Schrödinger equation transforms into a system of difference equations for the coefficients of this expansion, and the existence of a non-trivial solution to that requires vanishing of the determinant of the corresponding linear system. So I write this determinant here. So you have some denominators, but the denominators are meant just to make our determinant well defined. Otherwise, we will have elements of this matrix which will grow as we go away from the diagonal or in this direction. And then, looking at this determinant, we can sort of almost guess the final answer, the formula for the determinant. So, first of all, we may notice that this function is obviously periodic, less obviously even, and it has simple poles at plus minus omega modulo integers. And also we see that this function goes to tends to 1 as this parameter sigma, the exponent of monodromy, goes to I infinity. And already from these properties, it follows that delta of sigma must have, well, this form, so with some constant in the numerator. So now, in order to fix this constant, we can pick an evaluation of this delta at an arbitrary point. So, for example, at sigma equal to 0. So this is the idea. And now the vanishing of our Hill determinant is equivalent to this equation here. And so now look, so what you have on the left is essentially the trace function. The trace function associated to this red contour on the previous picture. On the right, on the other hand, so we have this sine squared of p omega. Omega is a parameterization of the zero mode of our potential. And we have delta of 0, so once again, so this will be some infinite determinant, but with no sigma inside. So basically, an infinite determinant which is completely determined by the potential. So in principle, this gives monodromy in terms of the equation data. Even though, well, infinite determinant is not easy to compute, but well, formally it gives a solution. Now, after this direct problem, we may be interested in a kind of intermediate problem, right? So I mentioned, so there is a direct problem to find this in terms of this, inverse to find this in terms of this. But now we can also say the following. So let's take one parameter from here, namely the position of the fourth singularity, one parameter from here, so it will be our sigma, and then everything else becomes a function of these two parameters. So in particular, our accessory parameter epsilon will become a function of t and sigma. And finding this function can be so we can solve this problem perturbatively, well, I think that for Heun equation this is not somehow in the literature, but in fact the method was introduced by Mathieu for Mathieu equation, and it is very straightforward, fairly straightforward to generalize this to Heun. And so then you obtain the accessory parameter in the form of such a perturbative series in 1 over t. So basically when this anharmonic ratio approaches infinity. And it is this function, accessory parameter, which turns out to be related to quasi-classical blocks by homological conjecture, which I am now going to explain. Okay, so, well, some basics here. So, Virasoro conformal blocks are some multivariate series that can be assigned to the following data. So, we need a trivalent graph, like in this example here. So the edges of the graph, they label different points on the real sphere. So we fix 3 of these points at 0, 1, and infinity. And also to each edge, we have to assign a conformal weight. So this, for us, it will be a generic complex number. And, CFT, you can view it as a black box, which gives you a way to compute this multivariate series. So we can compute this coefficients fk, either using Virasoro commutation relation, or using AGT correspondence, or using Zamolodchikov recursion, and so on. So there is some machinery which allows you to compute the series. And the important thing is that we have a very good intuition about the analytic properties that these functions or multivariate series should have. There is no proof, but very good physical intuition. So the particular case which will be relevant for Heun equation corresponds to this 4-point conformal block where we have this graph, 5 conformal dimension, and one more parameter which is the Virasoro's central charge. Okay, so now quasi-classical limit. So what is quasi-classical limit in this setting? So to explain it, it will be convenient for me to parameterize the central charge and conformal dimensions in a certain way. So I will trade C for the parameter B, okay? And I will parameterize conformal dimensions with this moment P. And the quasi-classical limit corresponds to sending all conformal dimensions and the central charge to infinity in such a way. So B goes to 0, B goes to infinity, but we require that the product of B and different momenta remains finite. So the conformal dimensions then scale in this way, and so these deltas are expressed in terms of these thetas in this way here. And just as this notation suggests, so these thetas will eventually become the exponents of local monodromy or this composite monodromy in different channels. So now the homological conjecture consists of 2 parts, basically. So first part is the statement that this series that we have for f exponentiates. So basically, if you take the log of f, you compute this again, once again as a formal series in different variables that you have. Then the statement is that every coefficient of the series diverges as 1 over b squared. So this is not obvious. Not obvious why it should be like that. But, well, there are some physical arguments that one can advance, but most convincingly, one can just compute a certain number of coefficients and just check that indeed all of them diverge in this way. And so this new series that we obtained in this way is called quasi-classical conformal block. And so now the statement of the second part of the homological conjecture is that the accessory parameter function that we have introduced before is nothing but the derivative of this quasi-classical conformal block with respect to this position of the fourth regular singularity.
Sorry, then if in your Heun equation this epsilon was 0,
yeah.
So then here what's going to happen? Because it could be, that you just had the potential without this extra red term that you have.
Okay.
So it means that epsilon was 0, for example?
But you have this variable sigma, right, as well. So suppose that you have epsilon equal to 0 in Heun, and for epsilon equal to 0, but with t equal to something, we have some non-trivial value of this composite monodromy. So if epsilon is equal to 0, so basically you can write the same equation, and it will become an equation for sigma. Sigma is a function of t. Setting epsilon equal to 0 does not simplify the equation at all. It's not like a distinguished value. Okay, and so now, so what we can do to check the conjecture? We just take well, generate the expansion of the quasi-classical conformal block using your favorite method. And, well, the coefficients of these expansions, well, they, so you compute these coefficients and you compare them with these coefficients coming from method by Mathieu, basically. And you see that everything matches like order by order to very high orders. Now, there is a fancy way of formulating the same result. So, in fact, like on both sides of this correspondence between the equation data and monodromy data, we have a symplectic structure. And with respect to and this Riemann-Hilbert map, it's basically a symplectomorphism, and we can say that the conformal block W is nothing but the generating function of a canonical transformation between these two pairs of coordinates. So I have not explained what is eta, but basically this is the Darboux conjugate of sigma, so some kind of twist coordinate on the space of monodromy data. Okay, so now in order to explain this homological conjecture, we need a few more basic ingredients of CFT. So one of these is so-called degenerate fields. So the main features of these fields that we need are the following. So first thing that one needs to know is that when we do the operator product expansion of a degenerate field with a generic Virasoro primary, then, well, in the intermediate channel, we can only have two possible dimensions characterized by this momenta, shifts by plus or minus b over 2. So this is one thing. And another thing is that conformal blocks involving such fields, they satisfy the so-called BPZ constraints. So once again, so this has already appeared in previous talks. So this differential constraints on conformal blocks, they are some linear PDEs, which are second order in the position of the degenerate field, first order in positions of other fields. And so in particular, if we just consider the simplest situation of 3 plus 1 point conformal blocks of 3 generic and 1 degenerate primary, then this PDE becomes an ODE, which is nothing but the hypergeometric equation, and so we can represent the corresponding conformal blocks by, we can just find explicit expressions for this. So now how to get to the homological conjecture? So the derivation or explanation actually relies on even more sophisticated conjecture. So the statement is this. So take like the initial conformal block with all dimensions going to infinity in the way I prescribed before, and add one degenerate field, so which is represented here by a dotted line. So this field is not heavy, so its dimension does not go to infinity, the quasi-classical limit, it goes to some finite value. And so there is some intuition, with physical intuition, which tells you that, well, this conformal block should have this WKB type behavior as b goes to 0. So what you have to notice is that the dependence on Z, on the position of degenerate primary, is not present in the leading WKB term. It only appears in the amplitude. So now if you accept this, this ansatz, then you can just plug it into the BPZ constraint. So the second order derivative with respect to z will remain in place, and the first derivatives with respect to positions of other fields, they will produce the terms like here, so some derivatives of w with respect to tk. So this is how this Heun equation or generalized Heun equation appear as a quasi-classical limit of BPZ. Okay, and so as I told you, so this rescaled external momenta of conformal blocks, they are related to local monodromy exponents. So the internal momenta corresponding, for example, to this edge here, they encode exponents of composite monodromy, and they parameterize the n-3 accessory parameter that you will have in your generalized Heun equation.
Just to be sure, so this classical limit is c goes to infinity,
yeah,
and it's Nekrasov-Chertashvili limit.
Yes. Yeah. Yeah, and so basically, why do I call this this guy W? Well, because it's twisted Nekrasov-Chertashvili superpotential. Okay, and so now comes another crucial thing. So now we want to go somehow to the connection formula for Heun. So we are asking a kind of more refined question. So we are not only interested in the accessory parameter, but we are also interested in the monodromy of connection properties for the solution of Heun equation. So for this amplitude, okay. And for this, I have to mention fusion transformations for a Virasoro conformal block. So, of course, one can write this fusion gradient transformations for arbitrarily complicated conformal blocks, but they take particularly simple form for degenerate fields, because precisely you can only have two possible dimensions in the intermediate channel. So if you have this 3+1 point conformal blocks, so the fusion transformation is nothing but this connection formula for Frobenius solutions of hypergeometric equation. At least you can interpret it like that. So this is the formula for the connection matrix that I wrote before. But the important thing here is that we can compute the analytic continuation of conformal blocks in the position of this degenerate primary using just elementary transformation. So basically, we can just forget about what we have here. So there can be some complicated trivalent graph here, but still, I mean, we will have this fusion transformation with the same hypergeometric connection matrix as before. Okay, so this follows from the locality of this fusion transformations. And so now you see, oops, sorry.
May I ask you a question?
Yeah.
So you have basically two solutions corresponding to the, for example, you have a momentum shift by p0 plus b,
Yeah.
maybe plus minus b. But if you take this quasi-classical limit, so b is a zero limit, I think. So then is it kind of degenerate limit in the end?
I'm coming to that.
Okay.
So it's like in two slides, basically. So this is precisely the point. So first of all, you should, I should maybe say that you should see this conformal, so you have a pair of conformal blocks here, a pair because we have plus or minus b, and a pair of conformal blocks here, plus or minus b in this channel. So you should think of this pair and this pair as a kind of quantum Frobenius solutions. to dpz, whatever it means. And so now I want to carefully take the quasi-classical limit of this to see if these are really related to Frobenius solutions of Heun. So this is what I am going to do now. So, and now look, what we have to do, so this is just a rewrite of the formula that I had before. Let us do an OPE of the degenerate primary with the field at 0. So we will have, it's better probably to look at this formula. So we will have some fractional power, which is a, well, it's an easy exercise to compute what should be here. And this fractional power will multiply a certain well, series, which is entire in Z. Okay? And which starts from this conformal block without degenerate insertions. Right? So now, already from here, you see that this is, in the quasi-classical limit, we have this guy, b squared, which goes to 0. We have b p naught, which goes to theta naught, so this local monodromy exponent. So we have exactly like the type of power that we had in Frobenius solutions, multiplying an entire series. So the only thing which differs from the Frobenius solutions of Heun is that this is not like correctly normalized. Yes? So it doesn't start with 1. And so now let us try to take this into account. So what we have to do is to take this leading term, multiplying the fractional power of z, and consider the effect of this shift by plus or minus b over 2. Here maybe I will write something. So we had something like P naught over here, or sorry, P naught, P1, P sigma, and then in the quasi-classical limit, we want to make this P naught big, right? So we have something like B minus 1 theta naught, B minus 1 theta 1. So now, what happens if we shift? And so this thing exponentiates. So this guy has the asymptotics, which has this form: 1 over b squared times w, and let me put here something like theta, sigma, theta 1, theta naught, to sort of underline what are the important variables here. And we have some probably prefactor, which is of order 1 in B. So let's call it, I don't know, B, okay, which depends on the same variables. Now, what happens when we shift P naught by B over 2? So effectively, for example, if we add to this thing epsilon b, so effectively this means that we have to add to theta naught plus epsilon b squared, right? And so now what we can do is just to, well, expand this w in powers of b squared, and so we see that the effect of this shift will be like an extra factor which will appear in the amplitude. Now, if we do this for the conformal block, for like the second base of Frobenius solutions with degenerate fields over here, then we will get a similar derivative with respect to theta 1. And so now, hopefully, you will be ready to accept this conjecture. So we go back to this standard normalized Frobenius solutions of Heun. We write this connection formula between two bases. And so the statement of these people is that well, the connection matrix is given by this hypergeometric expression which we had in the fusion transformation for conformal blocks with degenerate fields, and there will be some additional kind of twist coming from these shifts by halves of B. Okay. So this is a very complete formula, and in principle one can test it very easily. So you just generate a conformal block expansion. You find sigma. You find for this expansion the expansion of the composite monodromy exponent in inverse powers of t. You plug both this expansion and this expansion into the conjecture. And what you end up with is a certain series for this connection matrix in inverse powers of t with like, completely explicit coefficients. So they are not very nice, but still you can compute them to basically arbitrary order algorithmically, because well, it basically determined how many terms in the conformal block expansion you are ready to compute. And so the result will be given by some combinations of rational functions and polygamma functions depending on the that you have in monodromy. Okay, so this is the result, and now I want to explain how this can be obtained without any use of CFT. So basically, how to transform this into a more rigorous state.
Could you go back to the last slide of the previous section? Yeah, here. So now you have with the log C has this kind of T expansion.
Yeah.
So then, so following like AGT something, so this small fk can be obtained from some limit of the Nekrasov function. This kind of thing. Maybe this corresponds to instanton expansion in this sense.
Yes, of course. Yeah. But you see, why do you have these d gammas? This is a consequence of this hypergeometric connection matrix. So polygamma functions, they come from when you expand this in instanton parameter. So basically, to find sigma, you have to solve something like Matone relation. Okay, so you substitute the solution into here, you re-expand, and this is what you get in the end. So once again, the answer is not so nice, but it's like a completely explicit. It was immediately used in application. It was immediately tested numerically. So convergent series, by the way, not like in WTV. So the question is, how can we reproduce the series? Okay, so the idea comes from a very classical result by Darboux, which is roughly the following. So if you have a Taylor series of a function, let's say around z equal to 0, then you can tell a lot about the singularity structure of this function by studying the large order asymptotics of the coefficients. So here you have an example. So we take just this simple function. Taylor coefficients, they have this form. And so you see that the large order asymptotics has this fractional power of k, which is related to the fractional power branching at z equal to 1. Okay, and Darboux theorem is just a generalization of this observation in a way. So let me maybe explain this with the help of hypergeometric. So it's another example. Hypergeometric connection formula that I have just shown you in the first slides, but now we can obtain it using Darboux theorem. So we take the Taylor, so we have first of all this F21 around z equal to 0, which we know to be a linear combination of these two other solutions of hypergeometric equation. And the question is how to find C and D. So what one can do is just take the Taylor expansion coefficient of this F21, then analyze the large order asymptotics, just a very simple exercise, and then to compare with the previous example. So you already see that the theta, so this fractional power, will be this A plus B minus C. So this C minus A minus B over here. And so the coefficient D will be basically what you have over here. So this is probably the fastest way to solve the hypergeometric connection problem. But it works for like an arbitrary series for which you know the so basically what you need to know is that you have an entire series around z equal to 0, and somehow you know that the only branch points of the corresponding function inside a circle of a radius greater than 1 is z equal to 1. And so then you can determine like the leading coefficient in front of the corresponding fractional power by doing this large order asymptotic analysis. And this is precisely what we are going to do in order to study the connection problem for Heun. So one can, in principle, consider an arbitrary potential v of z with this function u of z here, which is holomorphic inside a circle of radius greater than 1. So if we introduce normalized Frobenius solutions just as before, then the corresponding connection matrix will be given by this formula. This is just a rewrite of this Darboux theorem, but now applied to differential equations. So what we do here is that we shift the one of the Frobenius solutions in such a way that it becomes holomorphic around the origin, and in such a way that one of the Frobenius solutions at z equal to 1 becomes holomorphic around z equal to 1. So we are now in the setting of Darboux theorem, and so we can then determine the coefficient in front of the second Frobenius solution by just looking at the large K asymptotics of these guys. Okay, and so let us now compute something for a simplified version of Heun. So this is the so-called reduced confluent Heun equation. So basically, instead of having like two second order poles and infinity, we have a third order pole at infinity. So this is there is an irregular singularity at infinity here. And so if this parameter lambda is equal to 0, then this becomes once again just the hypergeometric equation, and we know the answer. Right? So we know that the Taylor expansion coefficients in this case are given by these Pohammer symbols, And the connection function is this combination of gammas. So what we can do when we switch on this parameter lambda is the following. So we just introduce the rescaled coefficients to simplify. And so the differential equation, so this reduced confluent Heun equation, it can be transformed into a three-term linear recurrence relation for these coefficients at AK. Very straightforward exercise. And so this AK, they satisfy this relation over here. So once again, if lambda is 0, then all of them are just ones. But if lambda is non-zero but small, we can compute. So what we are interested in is the limiting value of the sequence, and we can compute this limiting value as a kind of infinite determinant. It's better actually to consider the logarithm of this limiting value and expand the corresponding determinant in powers of lambda. So then what you will get at different coefficients, so you will have some simple sums over integer k of some combinations of this beta k's are some rational functions of k. So basically, at each step here, at each order in lambda, you will have a sum which you can algorithmically compute. So basically, this will be given by once again some rational functions of parameters and polygammas. And so you can now take these expressions and just compare the predictions of this Trieste formula by Bonelli, Tanzini, Panea, and Dios. And you, as far as you can compute, you have a complete match. So here I discussed reduced confluent Heun, but for the usual Heun, it works in precisely the same way. Well, there is some combinatorial representation for these coefficients, but probably I will just show you the final result. So if you write the reduced confluent Heun equation in this form, then the connection matrix relating the two bases of Frobenius solutions at 0 and 1 is given by this hypergeometric piece and an expression which you can compute perturbatively in lambda. So this infinite fraction and sum, this is just a way to write the solution of this three-term recurrence relation. But actually, in practice, it works very simply. So if you are interested, let's say, in the approximation of this function up to, say, lambda squared, you just truncate this infinite fraction, expand, so then you will have some rational functions of k for which you have to compute the sums. And this produces all these polygammas and so on. So you can algorithmically compute any order in lambda here. And in the case of Heun, this is pretty much similar structure. So this is once again the potential. The analog of the parameter lambda is 1 over t. So recall that our t was greater than 1. And once again, so we have the hypergeometric part and some infinite fraction part, which you can compute. Okay, so I think I have to come to conclusions. So first of all, so was this formula for the Heun connection matrix in terms of quasi-classical conformal blocks correct? Yes, as far as we can check. So I think that for Heun we went up to order 5 in lambda and found a complete match. For reduced confluent Heun, one can go much further because the expressions are less cumbersome, maybe up to order 8 or something. So we have a complete match. Now, is CFT really necessary to solve Heun connections? No, because as you see, we can compute these perturbative expansions rigorously in a pretty elementary way, right? And in principle, this can be extended to irregular singularities. So what is there to prove, in fact? Well, there is still one interesting conjecture or fact to be proved. So, in fact, we can now forget about conformal field theory and define this W as a kind of integrated accessory parameter. Okay, so this the W defined in this way will be a certain function of T, the fourth singularity, of sigma, which is the exponent of composite monodromy in Heun, and of all of the local monodromy exponents. Okay? So now the statement, non-perturbative statement contained in this Trieste formula is that the logarithm of this connection function is expressed in terms of the same integrated accessory parameter, but now differentiated with respect to local exponents. So what does this suggest is that, well, we have to probably consider, so this should be probably related to this extended symplectic structure which was introduced by Bertola and Korotkin, where so usually when you consider the space of monodromy data, you fix thetas. Local exponents. But now the proposal is that so you have to allow for the local exponents to vary as well, and so you see that so this connection functions, they should be at least in some sense to be like conjugate variables to the thetas. Another conjecture that one may advance is a relation to Penlever-Sixtau function, namely to the connection problem for the Penlever-Sixtau function, where you seek to relate the asymptotics of the Stau function between a fixed singularity, for example, 0, and a movable zero, so movable pole of standard Penlever transcendent. Why? Because, well, these movable zeros are known to be related to Heun equation, and it is possible to, again, it was mentioned in one of the talks, I think, that it is possible to extend this Jimbo-Miwa-Ueno differential in all of the monodromy parameters, including this parameter theta. So in this way, in principle, it is possible to find the connection coefficient, the relevant connection coefficient, and so this connection coefficient can be conjectured to be closely related to this integrated accessory parameter, or if you like, quasi-classical Liouville conformal block. Okay, I think that's all I wanted to say. Thank you very much.
Any questions or comments?
I'm not familiar with the W here. Is it related? Should it be related to the fixed function here?
So the W.
The W function that you have here.
Yes. So let me write this like in a impressionistic way. So so you have an expression for the d log of tau, where you will have a differential in the Penlevet time. Let's call it x. So this will be like the Jimbo-Miwa-Ueno part. But there will be some contributions in local exponents. There will be contributions in sigma. So basically, all monodromy parameters that you have. So there is a formula like this. Now you can ask the following question. So one can look at the asymptotics of this tau close to the fixed critical point, x equal to 0. So it will be given by something like C naught x to sigma squared plus smaller term. But one can also look at the asymptotics of this tau function close to its 0. So it will be something like this: Ct x minus t 1 plus and so on. And well, in this definition, there is an ambiguity related to the fact that you can always add to this differential closed one form on the space of monodromy data. But if you now consider something like Ct over C naught, so the ratio, so this connection coefficient relating the two asymptotic regimes, then this is independent of this ambiguity. And so my statement, and in principle this guy is computable. You can compute the differential of this quantity, so the derivatives with respect to all monodromy data. So my conjecture, admittedly very imprecise, would be that so this guy is, well, the exponential of the quasi-classical conformal block up to some more elementary.
So in this case, t is corresponding to some zero of the tau function.
Yes. So t is a zero of the tau function.
A false regular singularity.
Mm-hmm. So usually I denote t by t Penlevet time, so here it might be a bit confusing, but yeah, so this is a different meaning. So this is the like the position of the fourth singularity in Heun.
But it's the Penlevet time, right? It's the same, no?
No. So in Penlevet, so your tau function will depend on x and monodromy, right? Now, at some point, so if you write tau equal to 0, so this will give you a priori an infinite number of solutions, x equal to something, and so let's just pick one solution, and it's known that, well, this value of Penlevet time is related. Well, so in this situation, the linear system associated to Penlevet 6 reduces to Heun. So basically, to go from Penlevet 6 to Heun, you have to consider something like 0 of the tau function.
So there's an additional apparent singularity, and you're taking the limit where the position of the apparent singularity moves to one of the mark points. Regular point.
Well, in this story, actually, I try to avoid. So you see, I'm not talking about something like Q, the standard Liouville transcendent. I'm only talking about tau function. If I were talking about Q, then Q of x, then so this reduction to Heun would correspond to zeros, poles, 1 points, and fixed points of this Q. But with tau function, it's much simpler. You just have to care about zeros. Does it answer your question, or it was like completely different?
I was thinking that with the inclusion of the apparent singularity, that second order differential equation will be what's coming out from the matrix differential equation, right? I can just write it as a second order differential equation, and then from that I can take the same limit, the semi-classical limit. I pick out this classical conformal block, which is more or less the tau function, but it's I should call it the Hamilton-Jacobi potential of the isomorphism moduli. I can formulate your conjecture in that using this S.
So it's just that I prefer to isomorphically deform the linear system instead of scalar differential equation with apparent singularities. But it's as you say.
Any other question? Okay, if not, let's thank the speaker.